we're going to preview exact differential equations and then work through a relatively simple example, at least in this video. Exact differential equations are important for at least a couple of reasons. First, many physical phenomena can be modeled with an exact differential equation, and here it will be highly helpful if you have taken a multivariable calculus course, because we can think of exact differential equations in terms of conservative vector fields, and in fact every inverse square field is conservative. And so Newton's law of gravitation, which is an inverse square field, in fact is a conservative vector field. Likewise, Coulomb's law, dealing with electricity, is a conservative vector field. In general, think about the law of conservation of energy. That's going to have to produce something that is conservative. In multivariable calculus, we learned that a vector field is conservative if the function capital F is equal to the gradient of its so-called potential function, lowercase f. Now, in 2 dimensions, let's say we have the vector field f of xy is equal to m I hat plus n j hat. That vector field is conservative if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. If that holds, we have a conservative vector field, and that is key. And every exact differential equation will maintain that equality. Secondly, from a more theoretical perspective, mathematicians have discovered that if you have a differential equation, if it's not exact already, there is out there, so to speak, some integrating factor to make it exact. Now, to be sure, finding that integrating factor may be extremely difficult, far more difficult than just solving that differential equation using another technique or method, but it's out there. Moreover, we should think about, in multivariable calculus, the idea of a total differential, because we can relate that with a differential equation. So let me jump into an example. So let's say we have the following example: y dx plus x dy is equal to 0. It is exact. First off, and we'll verify this in a couple of minutes, this equality holds. The partial of m with respect to y is equal to the partial of n with respect to x. Moreover, the differential equation is equal to 0, which is also important. And I'm going to tell you the solution from the outset in this case. It's xy is equal to c. It's always going to be of that form, where it's equal to some arbitrary constant. In multivariable calculus, what will that look like if we graph that? It will be a level curve. So the solution to an exact differential equation is going to be some level curve. Now, generally speaking, let's say we have m of xy dx plus n of xy dy is equal to 0. So this equation, which is a differential equation, is exact if and only if this equality holds. So notice that this y is the m of xy. This x happens to be this n of xy. So what is the total differential? So to review, it would be df is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. So if we take the total differential of xy, we're going to end up with this differential equation. We're going to end up with this left-hand side, namely y dx plus x dy. Additionally, because xy is equal to a constant, the total differential of a constant has to be 0. So we will get our differential equation just by taking the total differential of our solution. Moreover, we can relate this to gradients once again, by the way. So generally speaking, if we're thinking about applications, it's a good idea to think about time. So if we divide everything by dt, we would get df dt is equal to the partial of f with respect to x dx over dt plus the partial of f with respect to y dy dt. Now, if we know that it's equal to 0, that's going to be the same thing as the gradient of f of, let's just say, r of t dot dr dt. So once again, we're back with a gradient and a dot product, because here we have the gradient vector field evaluated at r of t. And here we have our tangent vector. All right, so that's pretty cool. But let's take this. Let's work with this. So let's first verify that xy, if we take the total differential, we will get this y dx, x dy. So let's first do that. And just to review, of course, uv prime, the product rule is just uv prime plus vu prime. So that's just the product rule. Okay, so we will get the total differential. We just want df, not df dt. So df is equal to the partial of f with respect to x. So this is what we're trying to solve. And we're working with it xy. And because it's a partial derivative, if it's the partial of f with respect to x, we will treat y as just a constant. All right, so we have uv prime. So u is just x. V prime is y prime with respect to x, so that's just a 0, plus vu prime, so y, times u prime, so x prime with respect to x is just a 1, dx plus, so now we want the partial of f with respect to y. We have uv prime, so x, y prime, so that's just a 1, plus vu prime, so y times u prime, so it's x prime with respect to y, just a 0, dy. So we have df is equal to y dx plus x dy. And of course, notice that is exactly our left-hand side of our differential equation. Great. And we have a constant, so the total differential is going to be a 0. But how do we go the other way? So we know what to do to get this differential equation, but how do we find the solution? So how do we go from here to here? So let's do that. So we have y dx plus x dy is equal to 0. That's the differential equation. So is it exact? That's the first question. So m of xy dx plus n of xy dy is equal to 0 is exact if and only if the partial of m with respect to y is equal to the partial of n with respect to x. Okay, so here we have m of xy, here we have n of xy. So let's just check this. So the partial with respect to y of y is just a 1. And the partial with respect to x of x is just 1. And of course, 1 equals 1, so we're good to go. Notice the right-hand side of the differential equation is 0. Good to go. All right, so how do we solve this? So the first thing to note is that this equality is true. Next, remember the total differential is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. So if we think about this total differential, this right here, the partial of f with respect to x, must equal m of xy. So these two must be equal. Likewise, the partial of f with respect to y must equal this n of xy. So this is not too bad. So the first thing we'll do, we'll say that the partial of f with respect to x is equal to m of xy, which happens to be a y. All right, let's just anti-differentiate. Both sides with respect to x. So the left-hand side, we get an f. The right-hand side, what do we get? We have multivariables here, so we have to be a little bit careful. We'll get a yx, but we'll have to add h of y. That's our constant. So if we took the derivative of h of y with respect to x, we would get a 0. So it does make sense to say we have h of y, not just a c. Okay, we're getting close, but what is h of y? If we solve that, we'll then have our answer. Well, we know that the partial of f with respect to y is n of xy. So let's do this. We can take, because here we have f. So let's just say that the partial with respect to y of f, what is that? Yx plus h of y is equal to n of xy, which happens to be an x. Great. So what's the left-hand side? So that would just be an x plus, so h of y, so that'll be h prime of y, the derivative, is equal to x. So the x's drop out. So we have h prime of y is equal to 0. Let's solve for h of y. So we can anti-differentiate both sides. So we get h of y is indeed equal to 0. So this means that we have solved the h of y in this f is equal to yx plus h of y. So we have yx plus 0 is equal to c. In other words, yx is equal to c as our solution. And that indeed is the solution. So it's pretty cool. There's a lot to be said in terms of vector calculus, and that can be a little bit confusing, to be sure. But the process to actually solve these is not too bad. I think when you first are introduced to this, it's a little bit tricky. But if you work through a few examples, things will click pretty quickly. And in the next video, I'm going to list explicitly some steps to solve these in a straightforward manner. And then in another video, I'm going to give a more proof-like presentation. But I hope this video has been helpful to you, and thank you so much for watching, and of course, good luck to you.